So previously we discussed the differences between analog and digital signals. Today we're going to review those concepts and do a deep dive on how analog signals get transformed into digital ones. So for our purposes, a signal can be thought of as a stream of information from one location to another. This stream can propagate through sound waves, radio waves, or in our case, electrically. Throughout the course of our experiments, we've used several different sensors that all transmit data electrically in the form of a signal. The signals that come out of our sensors do so in the form of an analog signal, where the data they hold go on infinitely beyond the decimal point. It's kind of like if you took a ruler and tried to measure how tall you were. You could measure in feet, but if you were 5'6", then you would have to round up or down by 6 inches, which is a considerable amount when every inch counts. So you instead decide to include inches, but maybe you are not exactly 5'6". Maybe you're 5'6" and 3 centimeters. And you could keep getting more and more precise from centimeters to millimeters to micrometers to nanometers, on and on, forever. This is what we mean when we look at the data in an analog signal, that the data held within is infinitely precise. So how do we analyze something that has an infinite precision? Well, this is where digital signals come in. Our processors are capable of quantizing these analog signals, which means they're approximating the values into a new digital signal. It's as if we were working backwards. Before we went from feet to inches, centimeters, millimeters, micrometers, nanometers, and now we're going back from nanometers to micrometers to millimeters to centimeters to get a value that our processors can handle. But instead of using meters, our processors use a value known as a bit, which is the smallest unit of data a processor can hold. So we're effectively converting volts to bits. But the way bits work is a little counterintuitive. An individual bit can only represent a 1 or a 0, on or off. That means if we only have one bit, there are two possible combinations or states it can be in, 1 or 0. But if we have two bits, there are four possible combinations, 0, 0, 0, 1, 1, 0, or 1, 1. And 3 bits can have 8 possible combinations. A way we can calculate how many states we can have is by taking 2 and raising it to the number of bits that we have. So for 2 bits, 2 to the power of 2 is 4. 3 bits, 2 to the power of 3 is 8. 4 bits, 2 to the power of 4 could have 16 possible states. Our ESP32 processors can handle up to 12 bits, so that's 2 to the power of 12, which is 4,096 possible combinations. So when an ESP32 converts an analog signal within the range of 5 volts to a digital one, it'll round 1.22 millivolts to a single bit. I got this by dividing 5 over 4,095. So to wrap this whole thing up, our analog signal has a voltage value that is infinitely precise. When that analog signal is input into our processors, it is quantized into a digital value using bits to round the data into a value that our processors are able to handle.